On Wednesday, we spent the majority of our time talking about the electronic structure of the atom from the standpoint of moving away from the idea of electrons in the circular orbits to the idea of electrons in these three-dimensional shapes that we call orbitals. Now, what an electron configuration does is an electron configuration tells us how the electrons of a given atom are distributed among the energy levels that are in a given atom. Now, we're not going to get too deep into the specifics of how to create an electron configuration. You're not going to be asked to build one from scratch. But what we will show you is how an electron configuration is constructed and how to use that information to identify the electron configurations of different elements. And for that, that mostly comes down to our periodic table. So if you have your periodic table, or if you have a periodic table on hand, I suggest that you get it out. There are some things that we're going to be able to draw on that table that are going to be helpful to us. And again, you can use these tables on your exams and on those quizzes, so that's definitely going to be helpful as well. What I want you to think about, though, what I want you to kind of look at are these. We've talked about the idea of sublevels. Sublevels meaning a group of orbitals that all have the same shape. The difference between the different orbitals is how they're oriented in three-dimensional space. So we talked about the S and how the S only has the one orbital. And we talked about the P and how the P has three. And those three orbitals are arranged in three different directions. One in the up and down, one in the left and right, one in the kind of in and out dimension. Three different directions, left and right, up and down, and one that comes at you and away from you. The D with its 5 orbitals, and the F with its 7 complete the description. And each one of those orbitals is capable of holding 2 electrons. So where we're going, what we're getting into is, this is how electrons ultimately are able to get away from each other so that their repulsion collectively doesn't cause the atom to just break apart. And this is where we're going to come to the periodic table. So in the periodic table, I want you to be able to identify a couple of different zones here. And I want you to be able to kind of look at those zones and use them as a map, kind of like a game of chemical battleship. If you're familiar at all with the game Battleship, you've got these ships on this gridded area. One of the grid markers is letters, one of them is numbers. And the whole idea of the game is that you guess a pair of coordinates where that ship is. Well, this is kind of the same way, only instead of coordinates A5, B3, C10, we're going to use our period numbers as descriptions of our energy level And these different zones of the periodic table so I've got the S zone here. I've got the P zone there. I've got the D zone here. And then I've got the F zone down here at the bottom. And so if I look at it from this standpoint, then this does represent kind of a weird game, but a game nonetheless of Battleship, where I can pinpoint, okay, 3S, and recognize that in describing 3S, I'm talking about one of these two atoms in that zone. How do I tell the difference between them? Position. This would be 3S1 because it's the first block in the zone. This would be 3S2, the second block in the zone. And so if I look at the electron configurations of sodium and its next door neighbor magnesium, what I will find is that sodium's electron configuration, 1s2, 2s2, 2p6, 3s1, is going to end with that battleship designation, 3s1. Everything else that came before describes the energy levels above, or in the case of the actual atom, the energy levels that are less energetic. And they follow the same rules as well. 1s, 2s, 2p, 3s. So electron configurations are drawn out of this idea. I start with my lowest energy, which is at the top of the table, and I build my way down to the highest energy, ending at whatever box the element I'm looking at resides in. And that box represents the last configuration of that particular element. If I look at magnesium, magnesium's configuration would have been 1s2, 2s2, 2p6, 3s2. And it comes from the same ideas. Starting here at the top, I have 1s. There are 2 blocks in that 1s area. The next group is the 2s. There are 2 blocks in that 2s. The next group being the 2p. There are 6 blocks. 1, 2, 3, 4, 5, 6 there. And then to get to magnesium, I have to have both of the electrons in the 2s. So yes, there's a little bit of complication here. This kind of takes a while to absorb exactly what's going on here. But what we can come across and come away with at the very end here is, if I clear everything off, the periodic table is set up in a very specific way. That very specific way matches the way that we describe our orbitals. S, P, D, and F, and the number of blocks in each one of those areas matches the number of electrons that are possible for that sublevel. The S is capable of holding 2 electrons. There are 2 blocks, 2 columns in that S block. The P sublevel is capable of holding 6 electrons. There are 6 columns, 6 blocks in each of those P levels. The D sublevel is capable of holding 10 electrons. Those 10 electrons can be represented by the 10 columns of the D block. The F sublevel is capable of holding 14 electrons, and we can see that that block has 14 columns in it, 14 blocks. Now, there are some interesting tendencies in here as well. First of all, we know that the D sublevel starts showing up at the 3rd energy level and beyond. Yet we only see it in this 4th energy level in terms of the rows. Why is that the case? Well, you have to remember something that we said on Wednesday. As our sublevels get more and more complicated, they also get more and more energetic. It becomes a lot more difficult to put electrons in there because they require more energy to go in there because they're more complex. Go ahead. And more. So n equals 3, n equals 4, n equals 5, n equals 6, and so on. Well, what we find is that in the Ds are actually just a little bit higher in energy than the S orbitals of the next energy level. And so the 4s actually is lower in energy than the 3D, so it fills first. So one thing that we have to know about the D sublevel is that we need to take the row number and subtract 1 from it in order to identify the orbital set, the sublevel, properly. So what this means is that this is actually the 3D. This is actually the 4D. This is actually the 5D. This is actually the 6D. All of those sublevels are offset by 1 because they are just a little bit more energetic than the S orbital, the simplest orbital of the next energy level. When it comes to F, that gets a lot more complicated. Again, we know that the F orbitals, the F sublevel, starts showing up in the 4th energy level, but the spike in energy required to put electrons in that 4th energy level means that we actually can slide a number of different other orbitals in between. So notice that this is actually in period 6. and this one's actually in period 7. And yet, they're not representing the 6F and the 7F. They're actually representing the 4F and the 5F. So for the F, what we're doing is we're taking the row and subtracting 2 from it. Now, the chances of us actually talking a whole lot about F sublevel chemistry is pretty remote. These substances there, other than uranium, I have incredibly limited interactions with most of those. You're talking to a guy who's been doing chemistry for about 20 years now. Other than uranium, which I've encountered in ionic compound form on a couple of occasions, and things like neodymium, which are in certain types of magnets. Most of those I've never seen, let alone worked with. And that speaks to their rarity. And especially once you get beyond plutonium, which is mostly lab created, all those other elements in there have only ever existed inside of a nuclear lab. They're artificial, they're synthetically made, and usually pretty unstable, don't last very long. So again, the point of all this isn't so that you can be given an element and say, okay, what is the electron configuration of sulfur? It's more, if I give you the configuration for sulfur, can you identify that that's what it is? So if I gave you the configuration, just as an example here, one S2, 2S2, 2P4, could you identify the element that matches that description? All you would have to do is follow along. Okay, 1S2 takes me there, 2S2 takes me there, 2P4, 1, 2, 3, 4. I'm talking about this element right here, which would be element number 8. This is a description of oxygen. That's all that I really am looking for you to be able to do. If you can do that, then we're on pretty solid footing for this particular concept. So can you work backwards and forwards? All right, any questions here? We will, Adria, we will. Monday's looking like a cleanup day where we're just going to kind of go over anything in Chapter 7 that we haven't talked about. Probably a good chance we'll have some review in there as well. All right. In this guided example, what is the last configuration for phosphorus? Well, again, can we pinpoint it to its particular battleship placement? So I look at it, I see, okay, it is here. I line it up. This is the 3rd energy level, the P block, and it's the 1st, 2nd, 3rd element. So its last configuration would be 3P3. If necessary, I would just fill in all the rest from there. So starting at the top, 1S2, 2S3, 2, 2p6, 3s2, and now we're into the block where phosphorus resides. It's 3p3. And so that's where we would take it. Now again, all we're looking for here is the last electron configuration. So the one that ends the configuration. And so again, we need to go to the table for that. So we are looking in particular at aluminum, scandium, zinc, potassium, bromine, and mercury. So let's switch over to a periodic table and look at that more closely. So aluminum. Aluminum is right here on my periodic table. If I am playing out my game of Battleship correctly, I've got the third energy level, the P block. So my sublevel designation would be 3p. My electron designation would be 1 because aluminum is the first element in that block. 3p1 is what I would need. For scandium, I'm right here. I'm in the D block. So I need to take my row number and subtract 1. So that would make this 3D. Scandium is the first electron in that, or the first element in that block. So its configuration would be 3D1. The next example, zinc. Zinc is in the same row, same block. So it's 3D also, but its position is different. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the last electron in that block. Its designation would be 3D10. Potassium. Potassium is also in this row. Since it is in the S block instead of the D, I take the energy level as it is. So it's 4S. And since it's the first electron, the first atom in that block, it's 4S1. Okay, Megan.
Can you write the whole thing for the D's?
What do you mean?
The whole configuration.
Can I write the whole? Oh, okay. So what the whole thing would look like? Sure. Okay, so for the scandium, starting at the top, it would be 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3d1. So if I was drawing a full configuration, I would just start at the top and just work my way down through the sublevels until I got to the element that I was looking at. And the thing is, all of the sublevels prior to this one are always going to be full, because in order to get to a partially filled or empty sublevel, I have to have all the ones before it filled. So I can always work off of the maximums for each sublevel from there. For the zinc is going to have a very similar looking configuration. Again, starting from the top, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then now we get to zinc's particular configuration, the 3d10. So what we're going to notice, and I'll even do it with the potassium here just to show off something. The potassium was 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. One thing that we should notice out of this is that within a given row, there are going to be some common characteristics as far as the electron configuration is concerned. Notice scandium, zinc, potassium, all three are in the same row. The only thing that is different about the three of them is what that last little bit of the configuration looks like. And so what we see often with these is that these common characteristics will actually be shorthanded. What we'll do is we will put in a designation that accounts for these commonalities so that we don't have to write them over and over and over again. Now, the thing that accounts for those is a noble gas, and we call those noble gas configurations. Now, the noble gas that corresponds to this designation ending with 3p6 would be what? What noble gas ends with 3p6? Argon. And so noble gas configurations would have us put that argon in brackets and then repeat the only part of the configuration that exists after that argon. So one of the ways that we can get around, especially as we get into elements that are further down the periodic table, one of the things that we'll get into a lot of is how do we make it easier? How do we shorthand it so that we don't have to write out all those configurations? And that's where the noble gases come in. What we are saying with putting argon in those brackets is we're accounting for those 18 electrons. We're saying, okay, in this energy level, they all have the same 18 electrons. Those same 18 electrons match the electron configuration of argon. Let's talk about what's different among them. And what's different is what happens after the argon. Scandium has 3 electrons after the argon. 2 of them are in the 4s, 1 of them is in the 3d. Zinc has 12 electrons after argon. 2 of them in the 4s, 10 of them in the 3d. Potassium only has the 1 electron after argon. Now, before we move fully on to electron configurations, let's go ahead and see how we understand this particular concept. Go ahead and give me the last configuration, not the full configuration, but just the last sublevel and number of electrons for bromine, number 35, and mercury, number 80. All right, so what do we say? For bromine, what is the last configuration in bromine? It would be 4p5. Again, how do we get that? Fourth energy level, P block. Bromine is the 1, 2, 3, 4, 5, the fifth element in that block, 4p5. For mercury, what do we got? Okay, it's not 6d10, it's 5d10. Okay, remember, for the D block, we have to take the row number and subtract 1. So you were correct, it's in the 6th row, but it's the 5th D sublevel. All right, any questions about this kind of view of electron configurations? Okay, so let's talk briefly then about condensed configurations, also known as noble gas configurations. These configurations, as I alluded to before, these kinds of configurations are common, and where we see them often is especially they're really valuable in the larger elements that have more electrons. But what we're doing in these cases is we are essentially substituting the electron configuration of a noble gas into the electron configuration of something else. We recognize that those two configurations are the same. And so instead of writing them both out, what we do is we substitute the name of the noble gas, argon, into the place of that electron configuration for iron, because in reality, these electrons represented by argon have very little to do with the physical or chemical properties of iron. These outer electrons are going to be much more responsible for how iron interacts with the world around it. And so that's where it comes from. Now, from a periodic table standpoint, you can always go to that just by simply rewinding. Take the element that you're looking at, rewind, go backwards until you find a noble gas. And that'll tell you which noble gas is going to belong in the brackets. So in the case of the mercury there, if I rewind mercury back, I would end up at xenon, element number 54. And that's how its noble gas configuration would start. Again, we're showing you this mainly as an informational clue. We're not going to ask you to build electron configurations. We're just asking you to recognize them. And part of that recognition is going to be in coming in contact with, well, wait a second. If I look at configurations in a given column, I'm going to notice some common features. So let's take the alkali metals, for example. In the alkali metals, I see that all of those configurations end the exact same way. Something S1. There's a pattern there. All of these end with an S1 configuration. Well, that's kind of interesting. Wonder what that means. I can take it a step further. Look at my alkaline earth metals. They all end with an S2 configuration. Every last one of them. Beryllium and magnesium, these end with S2 configurations. Not sure why potassium and rubidium are on here. Those are both alkali metals. I think these configurations actually match up. So let's cross these out because these are incorrect. 4s2 would match the configuration of calcium. 5s2 would represent the configuration of strontium. But we can see the same pattern still emerging. All of them end with the same configuration. Let's look at the halogens. Fluorine, chlorine, and bromine all end the same exact way. P5, P5, P5. All of the noble gases end with P6, just at different energy levels. So what we are driving toward is an overall idea of a family concept of elements. Now, we've talked about elemental families when we first talked about the periodic table. The alkali metals all behave a certain way. The alkaline earth metals all behave a certain way. The halogens all behave a certain way. The noble gases all behave in a certain way. What we're going to get into on Monday is start to put in some reasons for why. Why do those elements behave in that way? What is it about them that do so? And to understand that, we're going to need to talk about something called valence electrons and comparing those valence electrons with core electrons, electrons that are nearer to the nucleus of that element. So we're going to stop here for today. Monday, we're going to talk about valence electrons, and then we're going to use that to springboard into talking about some periodic properties. Because what we'll find is that all of these kind of fit in to tell the same story. And so that's where we'll go on Monday. I'll also address any questions that we might still have about electron configurations. Hopefully after you've had the weekend to kind of mull it over, it'll make it a little bit more sense. But if we need a little bit of time on Monday to talk about that as well, we will. Have a good weekend.